students, we have already studied analog to digital converters. Today we will be focusing on DAC, digital to analog converter. Okay, it's an output device. ADC was an input device. DAC is an output device. Function of the device: it receives the digital input from the microcontroller or the microprocessor and it converts it to the corresponding analog output. Okay, so DAC's function is exactly reverse of ADC. Now just like ADC, okay, DACs also have some important terminologies. But before going to the terminologies, let us see the different ways in which the DAC is constructed. DAC is constructed in two basic ways: the R2R ladder type DAC, R2R ladder type DAC, okay, and you also have the another type of DAC called as the binary weighted DAC. The most commonly used DAC in most of the applications is the R2R ladder type DAC. Now, in the third semester, you have already studied the structure of the R2R DAC. We are not going to go into the structure of this device. We are going to see the important terminologies related to DAC. Please come to this slide. Okay, what's there in this slide? Digital to analog converter is a device used to convert digital pulses to analog signals. Okay, so as I talked about two methods of constructing DAC, binary weighted and the R2R ladder type. Okay, mostly used is R2R ladder type DAC. Okay, now just like ADC, coming back to here, just like ADC, we have another important terms in DAC. In DAC also we have the term called as resolution. Now how was resolution defined in ADC? In ADC, resolution was defined as the number of binary outputs that the device is going to produce. However, in a DAC, the resolution is defined as number of binary inputs. Number of binary inputs to the device is called as resolution of the DAC. DAC is available in the resolution of 8, 12, 16 bits. Okay, so DAC is available in the resolution of 8, 12 or 16 bits. We will be studying the 8-bit DAC, which is commonly used IC is DAC0808, okay, also known as MC1408 ADC. Now this is commonly used DAC. Okay, we will be studying this DAC. Resolution, which is the most important term in a DAC. Come to this slide here again. Okay, so now this DAC, that is 0808. Okay, here as you can see from this slide, the digital inputs are converted to current. Now this DAC IC converts the digital input to the current form and then using a resistor to the I-out pin, we convert it to voltage. Now refer to this formula. This formula of I-out gives us the value obtained in analog. Now these are the digital inputs. How will the output be obtained? Output will be obtained as a discretized or crude waveform. Okay, the total current provided is called as I-out. Okay, it's a function of the reference current. I-reference commonly is chosen as 2 milliamperes. What is the value of I-reference? I-reference is commonly chosen as 2 milliamperes. The total analog, talking about the analog output current, how much current is generated. So the formula for finding out I-out is given by I-out is equal to I-ref. I-ref is called as the reference current, which is normally 2 milliamperes. Okay, now the input is in digital form. Okay, in a DAC, okay, if there are n inputs, then number of analog output levels, okay, number of analog output levels are 2 to the power of n. This is a very important concept that you must know. Okay, if there are n inputs, like for 8-bit DAC. Okay, value of n is 8. So the number of analog output levels in which you are going to get the analog output is 2 to the power of 8. That is, there will be total 256 levels in the output. Whichever way you want to take the output, there will be 256 ways in which, 256 steps in which you are going to get the output. So number of analog output levels, or you can call these as steps. Okay. So those are 2 to the power of n, that is 256. So we should always remember this before we go to the formula for I out. Okay. So as I was talking about, the MC1408 or DAC0808 gives you current as the output. So current I out is equal to I reference into D7 by 2, whatever is the value of this bit, plus D6 by 4 plus D5 by 8 plus D4 by 16 plus D3 by 32 plus D2 by 64 plus D1 by 128 plus D0 by 256. This is the formula to find out I out, that is the total output current, analog current for a given digital input. Okay. How to find out V out after this? After this, to find out V out, we just need to multiply. V out is equal to, okay, V out is equal to, okay, I out into VCC. I out into VCC. VCC common value is chosen as, okay, I out into the resistance. I am so sorry. We'll correct this. V out is equal to I out into resistance. This resistance value is commonly chosen as 5 kilo ohms. Resistance value is commonly chosen as 5 kilo ohms. So, for a particular binary input, we can calculate the number of steps in which we get the output. Also, we can calculate the output current if we know reference for current. And if we know the value of R, we can also calculate the analog output voltage. Okay, let's take an example. For example, if we choose the input as say 1, 1, 0, 0, the analog output current which is given by this formula. Now, let us take an example to understand it better. Suppose our digital input is this. Okay, this is our digital input. We want to find out the corresponding analog output voltage. Okay, so how will we do? We'll first find out I out. I out is equal to I reference. I reference value is given to us. We'll assume it as 2 milliamperes. 2 milliamperes into D7 by 2. What is D7? D7 is 1. 1 by 2 plus D6 by 4. 1 by 4 plus D5 by 8. D5 is 0. Okay. D4 by 16. D4 is also 0. Okay. Then 1. Okay. D4 is 0. D3 1 by 32 plus 0 by 64 plus 0 by 128 plus 0 by 256. So if we do this multiplication, we get the current around 1.56 milliamperes. This is the output analog current for this given value. Now we want to find out V out. So V out is given by our formula I out into R. Assume R is 5 kilo ohms. So we'll take 1.56 milliamperes into 5 kilo ohms. What we'll be getting? We'll be getting the output as around 7.8. You please verify this. You'll get the value around 7.8 volts. Okay. So given any value of a digital input, we can convert it into the analog output voltage, provided we know the value of current reference Iref and the value of the resistor R. Okay. Now if we have the input as all F, okay, if the digital input is amperes using the same formula, and V out you get around 10 volts. So it comes approximately 9.95 volts, which can be taken as 10 volts. This 10 volts is called as full scale voltage. What is this 10 volts? This is called as full scale voltage. Now why it is called as full scale voltage? Because our input is maximum. Input is FFH. So the maximum output that we can get for values of binary input as all ones is around 10 volts. 10 volts is called as full scale output. Okay, remember this. Okay, so this now what is this ADC or what is this DAC used for? This is used to generate different type of analog outputs for a particular digital input pattern. Okay, like we can generate a square wave, a triangular wave, a sawtooth wave. Okay, even a sine wave can be generated using a DAC. So before going to the generation of the different waveforms, let us see the connection diagram of DAC with microcontroller 8051. So let us focus on this slide. This is the connection diagram of 8051 with DAC 0808. As you can see, port 1 of 8051 is connected to the input lines of the DAC. Input lines of the DAC are D0 to D7. Besides this, you have VCC connected to 5 volts. You have V reference plus, just like in ADC, V reference plus, V reference minus. V reference plus is also connected to plus 5 volts through a resistor of 5K. V reference minus is always connected to ground. Okay. VEE and compensating network is used to hold the value of the analog output signal, because analog is continuously changing. Okay. Now we know that this IC gives you output in the form of current. What we want? We want the output in the form of voltage. So we connect a op-amp IC. You know this. This is the 741 LM741 operational amplifier. Here in the feedback path we have connected a 5K resistor. Okay. In the inverting configuration we get this particular is converted into analog output voltage. This acts as a current to voltage converter. Okay. So this acts as a current to voltage converter. So this diagram will be common for all the type of output waveforms that we are going to generate using the DAC. Now let's start with the different programs that we will be doing to generate different waveforms. So I'll keep this on this slide. Let us see the programs. So let us take the first program, that is generation of a sawtooth waveform. Now what is a sawtooth waveform? A sawtooth waveform looks something like this. This is the axis. A sawtooth waveform looks something like this. So how are we going to generate this waveform? Supply values of binary from 0001 up to FFH, then decrement, again start from 00, go up to FF, again decrement. This is what we want to do to generate a sawtooth waveform. Now the program for generating a sawtooth waveform using DAC is very simple. Just supply binary values from 0 to FF. Okay. Now I put these values at port 1. In the diagram we have seen port 1 is connected to the DAC. So I put the value 0 in the accumulator. From accumulator I will put it at port 1. So put 0 in accumulator, you can use move A, #00H, or you can go for clear A. Clear A will also do the same thing. Make accumulator 0. Make accumulator 0. Where do we want to send this value? We want to send this value at port 1. Move P1, A. Send the value at port 1. Now what we have to do? We want 00 to become 01. For this what we will do? We will give INCA. INCA, increment A to make it 01 and repeat the process continuously. So I will give SJMP L1, L1 over here and end. Okay. So when it goes to FF, FF plus 1 is 100. 1 is discarded, the value again drops down to 0. This is how we are going to generate a sawtooth waveform using DAC. So we were doing programming of DAC. We have seen one program to generate a sawtooth waveform. Now suppose if you want to generate a reverse sawtooth waveform. Okay, if you want to generate a reverse sawtooth waveform, it will be generated like this. The waveform will look something like this. Okay, we will start from FF, go down, again increment, again go down. So we have to initialize accumulator with FF, let it decrease to 0, again make it increase to FF, again reduce it to 0, and so on. So we have to write a program for doing this. So what I want to start with FF. So I'll give move A comma hash 0 FFH. Right? Now we have seen in the diagram that DAC is connected to port 1 of the microcontroller. So I put this value at port 1, move P1 comma A. Put the value at port 1. Next what we have to do? We have to decrement this value. In sawtooth waveform what we had done? We had incremented the value. Now what we will do? We will do decrement A. So what will happen? FF minus 1 FE, FE minus 1 FD, and so on. This process will continue till it becomes 0. Now what happens when 0 minus 1 is done? 0 minus 1, okay, we are subtracting a larger number from a smaller number. So 0 minus 1 will give me FFH, 2's complemented value of 0. So we will get directly FF, we need not increment the accumulator. Okay, so what I will do, I will give a SJMP here and L1 will be at this instruction. So this is the small program that will generate a reverse sawtooth waveform on the screen. So if you feed this program, you will observe that a reverse sawtooth waveform is generated. This is how we are going to generate a reverse sawtooth. I hope you have understood a forward sawtooth and a reverse sawtooth. If you have understood these, let us try to write a program to generate a triangular wave. How are you going to generate a triangular wave? Okay, so a triangular wave will be generated like this. It will be something like this. I want to generate a triangular waveform. So what I have to do? I have to start from 0, go up to FF. But what will happen if I increment again? Okay, this will drop down to 0 here. We don't want this to happen. What do we want? We want FF to gradually decrease to 0, 0 to gradually increase to FF, and again FF to gradually decrease to 0. So we have to wait here. How are you going to write the program? Suppose you start with 0. So how do you start with 0? Move A comma hash 00 H, or simply you can start like this, clear A. Okay, clear A will make accumulator 0. Put it at port 1. Okay, initial part will be same as sawtooth. Okay, then what we had done in sawtooth, we had incremented A. Increment A. The same thing we are going to do here. But now we are not going to do this forever. We are going to compare with the value FFH. So for that we have which instruction? C, J, N, E. Compare and jump if not equal. What is to be compared? The value present in accumulator to be compared with 0 FFH. Okay, I'll give the label here itself. Okay, do I need to give here itself? Okay, compare A with FF. A has 0, not equal. What you have to do? If the value of A is not equal to FF, keep on outputting the value at port 1. So I'll put my label over here at move P1 comma A. Now, once the value reaches FF, this condition will be false. Okay, so we cannot branch. We'll have to execute the instruction written in sequence. How are we going to do this? Before branching, okay, if the value of A becomes FF, move the value again at port 1. That means output FF 2 times on port 1. Okay, first when it goes here, it waits. It keeps it at FF and then you have to gradually decrease. Now I'll give DECA. Now what will happen? FF will become FF minus 1 FE. Now FF will become FE. If you would have decremented here directly or incremented here directly, we would have gone to this point. We don't want this to happen. We want this to happen gradually. So decrement A, and then what you have to do? Do you have to do this continuously? No. Decrement A, output it at port 1 again. Output it at port 1, but this also not to be done continuously. So again I give a CJNE, compare and jump if not equal. What? Content of accumulator this time with 00H. Has it reached 0? If it has reached 0, then what you have to do? You have to, what you have to do until unless it is not 0, you have to output it again. So what I'll have to do? I'll have to output this value again at port 1. Okay. Now you will ask, why do you need this always? No, we can skip this. Even if you skip this, there is no problem. Okay. You can skip this instruction if you want. Okay. Move P1 comma A, decrement A, compare, go on outputting this. So what will happen? 0 to F, wait, F to 0, wait, 0 to F, wait, F to 0, wait. So in this way, at the end, a triangular waveform will be generated. Now, do you want to generate only one pulse? No, you have to repeat this continuously. So I'll give a SJMP L3, and where do you think L3 should go? L3 should go over here. It should start all over here again. Okay, so you can either give it over here. Okay, you can give L3 over here, start from the first instruction again. Understood? In this way, you can generate a triangular waveform on the screen. Okay. After this, what we are going to do? We are going to write a program to generate a square wave. Okay. Now, how will you generate a square wave? Okay, square wave generation is pretty easy. It, however, requires one special program for delay. Now, how does a square wave look like? How does a square wave look like? You can start with 0 here. I'll use another color pen so that it is properly visible. 0, F, delay, 0, delay, F, and so on. So 0, 0, give a delay, F, give a delay, again 0, give a delay, and so on. So you have to repeat this pattern. So the program is pretty simple. Simple, start with clear A, give accumulator 0 and output it at port 1. This much we know by now. Okay. And we want the microcontroller to wait here because we want 0 for a long period of time. So I call a delay program over here which will make the microcontroller wait. Once we are done with this, I'll give, either you can give move A comma hash 0 FFH, or you can also do CPLA. What will CPL do? CPL will complement accumulator. So 0 is at every position of 0, it will be replaced by 1. So here if accumulator is 0, CPL you give, accumulator will become FF. Either you give this instruction or you go for move A comma hash 0 FFH. Move port 1 comma A. You can repeat this again. Port 1 comma A. Give a call delay once again. And you can do this continuously. Okay, you can do this continuously. So you can start over here again. Now you ask, doesn't this look lengthy? Yeah, it pretty looks lengthy. We can shorten this. How are we going to shorten this program? Okay, we can shorten this program in a very simple manner. Okay, whatever may be the content, if you want, you can give simply, you can start in the same way, clear A. Okay, move P1 comma A. Fine, give a delay. This you can't avoid. You always have to give a delay. Give a CPLA. give a CPLA, complement, 0 will become FF, okay, and give a SJMP over here, come over here. So CPL, that means it will be made FF, give a delay, again complement, FF complement will be 0 again. So you can do in this manner also. What is the thing that is remaining in the program? It's remaining delay program we have not written yet. Okay. So write down any standard delay program using one DJNZ or maybe using 2 DJNZ. Whichever way you want, you can write down the standard delay program. Okay. So in this way, you can generate a square wave using DAC. Okay. Now these are pretty simple, right? A sawtooth wave, a triangular wave. You can even generate a staircase waveform. Okay, but for that you require to understand the size of the staircase and so on. That becomes a little complicated. Now the most important program in DAC, that is generation of sine wave. So far we have seen DAC programs to generate different waveforms like sawtooth, square, triangular and so on. Now the most important part, how do we generate a sine wave using DAC? To generate a sine wave using DAC, how does a sine wave look like? A sine wave looks like something like this. Okay. So whatever input values we are going to feed to the DAC, we should get an output like this. This is our expected output. Okay. This is our expected output that we should get. But do we get an output as smooth as this? No. We always get the output in the form of steps. Now how is the output obtained? I will tell you. It is obtained like this. This looks like a sine wave, but it is not a sine wave. See, you can see if you reconstruct this signal properly, it looks like a sine wave. Okay, but this is not an actual sine wave. It is called as a crude sine wave. C-R-U-D-E, crude. It's called as a crude sine wave. Now, why do we get such type of output? Because we are going to feed values. We are going, how we are going to get such type of waveform or such type of waveform as output? We are going to feed values of angles from 0 to 360 degree. Okay. Corresponding to that, we'll find out the voltage magnitude and the values to be given to the DAC in decimal, so that at the output we get like this. Okay. So this wave that is generated is called as a crude sine wave. Now what are the values that we will get? The values that we'll get will vary from -1 to +1 for the angle of theta between 0 degree to 360 degree. We have to take sine theta. Okay, we'll take sine theta. We want to generate a sine wave. We'll take sine theta. Okay, and the values will be varying from -1 to 1 for different angles. So 0, 1, 2, 3 up to, like this we are going to put the values of the angles to get the output as a crude sine wave. Please refer to this slide here. Now here there is a formula that is given on this slide. On this slide there is a formula given. Read the content on the slide. To generate a sine wave, we first need a table. So what we need to find out values of angles. Now what are we going to do by finding the values of angles? We are going to prepare a table of the values. And where are we going to load the table? The table will be loaded in lookup table. It is called as a lookup table, which will be loaded in internal EEPROM of 8051. That is the 4 KB internal EEPROM of 8051. We are going to load this lookup table. So to generate a sine wave, we need to load a table whose values represent magnitude of sine of angles between 0 to 360 degrees. As I told you earlier, the values vary from -1 to +1 for 0 to 360 degrees angles. So to achieve a full scale output, I had talked about a full scale output, okay? Full scale output is normally 10 volts. To get a full scale output of 10 volts, we use this formula. V out equal to 5 volts plus 5 into sine theta. So what formula are we going to use? we are going to use the formula V out equal to 5 plus, okay, 5 into sine theta. Okay, so if the value of angle is 0 degrees, V out will be 5 plus 5 into sine of 0. What is sine of 0? Sine of 0 is 0. We know this, sine of 0 is 0. So what output will we get? We will get 5 volts as my output. Similarly, if the value of angle is say 90 degrees, if the value of angle is 90 degrees, or let us take say 30 degrees, then what will be the value of V out? V out is equal to 5 volts plus 5 into sine of 30. Okay, sine of 30. Okay, so according to the value of sine 30, what is sine 30? Sine 30 is half. Half means 0.5. Okay, so what will we get over here? 5 volts plus 5 into 0.5. So this will give me a value around 7.5 volts. But can you send this value to the DAC? No, you cannot send these values. You cannot send 5 volts. You cannot send 7.5 volts. What are you going to send? You are going to send value in decimal corresponding to this voltage. Corresponding to this voltage, you are going to send values to the DAC in decimal. So, values to be sent to DAC in decimal. In decimal, what values are you going to send to get such output? For this, the formula is V out into 25.6. Now you'll ask from where this 25.6 has come. See, the DAC is 8-bit. DAC is 8-bit. So, output levels or output steps are 2 to the power of 8, that is 256. Full scale output is 10 volts. So, 256 divided by 10 gives me 25.6. From here this value has come. Now what are you going to do with this? Values to be sent to the DAC in decimal is calculated as V out into 25.6. So for the angle of 0 degrees, what is the value to be sent in decimal? Let me represent this value by x, suppose. Let me represent this value by x. What will be the value of x here then? Here it will be 5, okay, into 25.6. Like this. Okay. Similarly, for angle of 30, the value of x will be 7.5 into 25.6. We will get a value and we are going to put that value. Now you will ask, how do you remember all this? So what are you going to do? You are going to write down the formula. If the problem comes in the exam, write down the formula and then from the formula prepare a table. Refer the slide over here. Okay. See, according to this formula, we have already prepared a table. Now where are we going to load the table? Now how are you going to load this table? You are not going to load everything from the table. You are going to concentrate on this last column. Values to be sent to the DAC equal to voltage magnitude into 25.6. This was what I was talking about. For angle of 0 degree, the value to be sent is 128. For angle of 30, 192. See, these are the values, V out values. Okay, we have already calculated this using the formula. So, values to be sent in decimal will be this value into 25.6. So, 0 degree 128, 30 degree 192 and so on. So, these are around 12 values. After 12, the values again repeat. So, what are we going to do? When we do assembly language programming, we are going to put these values in the form of a lookup table in memory. Which memory? On chip EEPROM memory. So, let us write down the assembly language program now. I hope you have understood how do we generate the values corresponding to the generation of a crude sine wave. So let me write down the assembly language program. Now as I have told you, you are going to put these values into on-chip EEPROM memory. So I can start from any value. I suppose take 300H. So what I do, I give org 300H and then suppose I name this as a table, okay, DB, and I put all the values over here. Which values you are going to put over here? You are going to put the values to be loaded into DAC in decimal. That is 128, 192, 138 and so on. You are going to load all these values. Now I am not writing all the values here. You are supposed to complete this. So what will happen? At the address 300H, the first value is already loaded, 128. This corresponds to the angle of 0 degrees. At 301, the value loaded is 192. This corresponds to the angle of 30 degrees and so on. So what are you going to do? You are going to do it like this. So this is what your table will be like. Now you have to start with your program. So program will be loaded from 0000H. So I will give 0000H and then now this table is loaded in on-chip EEPROM. On-chip EEPROM address I have to put in DPTR. Move DPTR comma hash 300H. I'll put the address into DPTR. Okay. Take the value from here and load it. But how many values? After 12 values, the values repeat. So may I take a count of 12? Okay, take a count of 12. From where 12 has come, these values are 12 in number. So I take the count as 12. Okay, and I start with the first one. So I again take clear A. I clear the accumulator first. Put the value from on-chip EEPROM into accumulator. So in that we have to give values or output values to the DAC in decimal, which will correspond to the angles from 0 to 360 degrees to generate what is called as a crude sine wave. So what are we going to do? We are going to put these values in on-chip EEPROM memory. Let me take the address suppose as 300H. Okay, I'll give the name as table suppose, anything you can give. Okay, DB. The first value 128, 192, 238 and so on. These are around 12 values. So we will prepare a table. So what will happen in on-chip EEPROM from the address 300H, each value will be stored. Okay, so 128 will be stored in memory at 300H, 301, 192, 302, 238 and so on. So different values will be stored in memory from these addresses. Now our main program will start from 0000H. So we will put it like this. Now 300 is the address of lookup table which has to be loaded into a register. So what I will do, I will give move DPTR comma hash 300H. Load DPTR with 300. I will load DPTR with 300. Now what I have to do? I have to take the value from here where into accumulator. I will put the value into accumulator. So what instruction will I give? Move A comma. Now since this is on-chip EEPROM address, I will give move C A comma at the rate of A plus DPTR. But now you will ask, for this A should be 0. We have not given an instruction here. So in between you can give a CLRA instruction. Clear A, then put the value into accumulator from this address 300. So accumulator will be loaded with 128. Where do we want to output this value? This value is to be outputted at port number 1. Put the value at port number 1. Increment DPTR now because the next value is stored at 301. The moment we do this, DPTR points to 301. And now we have to repeat the process again. So DJNZ, because we have not given a count here. We need to give a count. We cannot repeat this continuously. Let me put a count value somewhere here suppose. So I will give move any register. Suppose I give R0 comma hash 12. Now from where this 12 has come? These are around 12 values. So I have taken the count of 12. So I will give DJNZ R0 back. Where do I need to go back? I need to clear accumulator again. Otherwise, accumulator will have the original value. So I'll come back over here and we'll repeat this again and again and again. SJMP, say L1. Where will my L1 come? L1 will come over here. Reload the count, reload the PTR and so on. So like this you can write down assembly language program. Now once you have understood assembly language program, writing a C program is pretty easy. I hope you have understood assembly language program. Now let us see the C version of this program. How are we going to write this C program? I declare a variable called as array variable. So I'll include the header file, hash include reg51.h, include the header file. Okay, and now I'll declare, I want to put the values at port 1. So I'll declare a variable SFR, say x equal to port 1. And now I do the initialization. For this you can do it either in the main or outside the main. So whatever way you want. Suppose I do in main, void main, okay, unsigned. I'll declare this with the data type unsigned character, say y. Okay, but now is this a simple character? No, it is a character which is a array type, character array. What I am going to put over here, all the values 128, 192, 238 and so on. All the values I am going to put over here. Let me initialize this variable y. Okay, and then I initialize one more variable, unsigned character z. Unsigned character z. I have to repeat continuously, so I will give while 1. While 1, I have to change the value of this character z. Z equal to 0. Z less than how much? These are 12 values. So z less than equal to 12 and z plus plus. What am I going to do in this? In this what I am going to do is I am going to take the value of x. X is equal to, now this is z. Okay. And this variable that I have used over here is y. Y of z. That's it. Finish. This is how you are going to generate a sine wave using DAC. So with this we finish with data converters, ADC and DAC. In the next lecture we will see interfacing of motors.